Alright, these are the AP1 UCM recorded notes or circular motion notes. Hopefully, there are 15 slides. Hopefully we'll be able to get through it in a good amount of time, in a short amount of time. Alright, circular motion equations that you need to know. Looking at your formula chart, you should see the F equals 1 over T formula, which does also equal, or T equals 1 over F. They are reciprocals of each other. On your formula chart, it actually has it as T equals 2 pi over an omega sign, which we'll talk later. Yes, that's my lowercase omega sign. So, for angular speed, which we'll talk about later in the next unit. And then we have equals 1 over F. So you do need to know that period and frequency are reciprocals of each other. You also have the formula of, you don't have this formula, but an equation that you need on your, that is V equals 2 pi r over t, which is really just V equals d over time, because velocity is distance or displacement divided by time, and the displacement when we're talking about circles is the circumference of a circle. Now the circumference of a circle is 2 pi r, which is on your formula chart, and divided by t, which we're saying is the period of the rotation. So V equals 2 pi r over t is a circular velocity motion formula. You could also then say that V equals 2 pi r f, because since f and 1 over t are the same thing, you could rewrite the formula and look like that. So it's important that you are able to use these formulas and use your circumference and your displacement and know that period and frequency are reciprocals of each other. Anybody remember these? They were super fun. They're actually great examples about circular motion. There's not very many of them anymore because they've gotten a little bit dangerous. But if you remember these, you can definitely think about how you felt when you spun around, and it'll help explain a lot of the things that we're going to talk about. So uniform circular motion. What is that definition? It is motion along a circular path in which there's no change in speed, only a change in direction. So, since velocity is speed and direction, we will be able to talk about whether it's accelerating or not, but the speed is going to stay the same. So there's a constant velocity that is tangent to the path, meaning that if it broke off of that string, instead of going in a circle, that speed that it would fly off at would be a straight line path, and that is tangent to the circular path, but it would have the same velocity the whole time as it went off in that direction. There is a constant force towards the center, which is going to be known as our centripetal force. Alright? And the question is if is there an outward force on the actual ball as well? Well, when we're talking about uniform circular motion, the question of an outward force can be resolved by asking what happens really when the string breaks. If the string breaks, it goes flying off in a straight line path that is tangent to the circle. So the ball moves tangent to the path, not outwards, as you might expect it to. Since it doesn't move outwards, there is no outwards force. So when the central force is removed, then the ball just continues in its straight line path. So the only thing that's keeping it in the circle is that force that's going towards the center of the circle. Once that force is no longer there, it just travels in a straight line, which means that there's no other forces involved. So centripetal force is needed just to is needed to change its direction so that it stays in a circle. If there's no centripetal force there, then it just stays in a straight line path, according to Newton's first law. So, centripetal acceleration, this is another definition that you need to know. An object experiencing uniform circular motion is continually accelerating. The reason it's continually accelerating is because of the direction and the velocity of the particle moving in the circle that has a radius r are shown at two different instances in the figure. The vectors are the same size because they have the same magnitude value, and the velocity is constant when we're talking about the magnitude, but the direction is changing continuously. And since the direction is changing, that means that it is accelerating because the velocity is changing. The speed is staying the same. The velocity is changing, but only the direction of the velocity is changing, not its magnitude. So to calculate the centripetal acceleration, we will use the linear velocity, or that tangential velocity that we're flying off at, and the radius of the circle. Now this formula is on the formula chart, and it's listed exactly as it appears. A with the subscript c means centripetal acceleration, which equals v squared over r. Now that v squared can have multiple substitutions, and we talked about that v formula a minute ago. Now we could substitute in our 2 pi r over t, or we could substitute in our 2 pi rf. So if we did that, we would get a formula that says, actually this would end up being a capital T, as we could say 2 pi r squared over r, or over, so it would be our 2 pi r over t squared over r. That would be one way to write it. So when we distribute the squared, we end up with our 4, our pi squared. We end up with r squared, which will end up canceling out one of the r's, and that's why we have 2. We have 4 pi squared r over t squared. We could also have said 2 pi rf squared over r, which when we actually distribute the squared, we can then say AC equals 4 pi squared rf squared. And again, the r would cancel, the r squared in the numerator, one of those would be canceled out with the r that's in the denominator. So there's lots of different ways to write it. These are some shortcuts, but you can use that velocity formula to make sure that you remember that. So let's talk about centripetal force then. And we're there on my merry-go-round. The inward force necessary to maintain our uniform circular motion is described as centripetal force. From Newton's second law, the centripetal force is given by F equals ma, but we add the subscript to c when we're talking about centripetal force. So we could also then substitute all of those acceleration formulas in and get it written like this. So we can write mv squared over r, and then we can substitute all those v formulas in and get that formula expanded 2 other ways. So just make sure that as you're expanding things, or as you're inserting other formulas in the formulas, that you cancel things out properly and put all your variables in place. So like a ball on a string, satellites are an example of uniform circular motion. They travel around us, and typically they're what we call, if there's just only one speed that a satellite can have, then it'll remain in orbit at a fixed radius. And the gravitational pull of the Earth actually provides a centripetal force, so it acts like an invisible guideline for the satellite, so that it'll travel in that same space over time. So when we get this, we could end up with satellites will encounter that inward force and accelerations, and the tangential velocities will be involved. So we could actually talk about the satellite and the Earth having a gravitational force with each other, and use our G equals m1 m2 over r squared formula. We could also talk about the centripetal force formula, which is now F equals ma, and we could put those formulas equal to each other. This is where I come up with that formula, that saying again of a force is a force is a force. So if the centripetal force is caused by the attraction force between the two, then you can set these two equal to each other. If we can set them equal to each other, and even expand it out, our centripetal force formula as mv squared over r, then we end up with this formula. And we can cancel the m's out, and we could use because that's the mass of the actual satellite, and one of the r's would cancel out, and so we would end up with that we could solve for the actual velocity that this satellite needs to be going to stay in that path around the Earth. So all the communication satellites that are sent up into orbit actually have to calculate this. And so they have to calculate how far they have to send them out, as well as what speed that they're going to need to be able to accomplish in order to continue in that pathway. So we can end up with V equals the square root of G, which is on our formula chart, that capital G is, then the mass of Earth, which we know, and our R value, divided by our R value. So, interesting things that everybody does know to get all those satellites up in orbit around the Earth. So we can also talk about what if the circular path isn't exactly a flat horizontal circle? What if it is what we call more conical pendulum? It consists of a mass that's revolving in a horizontal circle of radius r at the end of a stream, but it's at an angle of some sort, so it looks more like this, okay, when we talk about it. Now, if that's the case, we do have to talk about some tension forces, we can talk about gravitational force, we can talk about angles, and then we can talk about components of tension times. So tension times the sine of theta would actually end up being our centripetal force. That would be our centripetal force to the center of the circle. And then if we knew that R value, we could do some things with it. So that becomes important that you think about it as component forces and triangles and things like that. We could also then know that if we had the weight would be the same as our t times our cosine theta. So if we needed to find some values, we could find some different values doing different things. So think about the components that you know, and how we dealt with tension, and how we dealt with weight force, and now we'll be applying to centripetal. So the inward component of the tension of t sine theta would give you your needed central force or your centripetal force. So the angle and the velocity can be found a lot of different ways. So we could solve two equations. We could say t sine theta equals our centripetal force, which is our mv squared over r. And so we could also say that t cosine theta equals our mass times our gravity. So believe it or not, when you use your t sine theta and your t cosine theta, you can create that t's will cancel out, and the sine theta divided by the cosine theta actually gives you tangent theta. So we can make this to where we set these equations over each other, and when we do that, we come up with the equation tangent theta equals v squared over gr, okay? The masses would end up canceling out. So really what I've done is I've just taken these formulas and done that with them. And so I end up with tangent theta equals v squared over gr. So if I'm going to do this example in class, this is not actually one of them that I'm going to do on the notes. So I'm going to pass through this real quick. So again, our circular motion equations of our F equals 1 over t, our V equals 2 pi r over t, our V equals 2 pi rf, our tangent theta equals v squared over gr, our V equals the square root of g me over r. We have our F equals mv squared over r, our F equals ma, our A equals v squared over r, and our A equals 4 pi squared times r over capital T, that should just be capital T, period, squared. There's other forms again of the manipulations, lots of different ways that we can use these. So lots of formulas. So we'll do a lot of examples in class or next time we're in class and we're taking notes. Have a great day.